Hi, I'm Aurora, and I will present a joint work with Cremers and Alexander Dax on the formal analysis of the security protocol and data model. We will first start by seeing why does the industry needs yet another new protocol. So as we know, computer platforms are constructed by a set of components. In the classical setting, these can be hardware components connected over the wires, such as the CPU, GPU, memory, and other external devices. And in the cloud computing, this can be multiple servers distributed across multiple locations, and then they need to communicate with one another. And additionally, these components might also have mutable configurations running in them. So this means that their firmware gets updated, or they can have reprogrammable microcode running. And due to this mutable or dynamic nature of each of these components, this means that they become a potential attack vector for the platform security and integrity as a whole. Take, for example, that one of these components might be running compromised firmware, or there is an untrusted device that is connected to the platform and, for example, can get access to confidential information because two components are sending unencrypted data over the wire. And at this point, then the question is whether the platform can then have some security guarantees, so the vendors can have some security guarantees of the platform that they are running, even though the components are from different multiple vendors and potentially there is an insecure wire. And to answer to that question, then DMTF, an industry standard organization, developed the security protocol and data model. So DMTF has members, some of the major names in the IT industry, such as IBM, Cisco, Apple, Microsoft, and so on. And SPDM has also seen a lot of support also by other standards groups, such as USB, Trusted Computing Group, and so on. And all of these names that you see here on the screen have either already deployed SPDM in their products or plan to do so in the near future. So we will now see what is SPDM. So SPDM can be defined as a two-party protocol for securing communication over the wire that has three goals. So within the platform, it needs to provide for authentication of hardware identities, it needs to allow for measurement of firmware identities, and finally, it needs to allow the two parties to be able to establish a secure session and then to allow them to exchange data in a confidential way while also preserving the integrity. And we will now see like a quick overview of what does the SPDM protocol looks like. We can divide SPDM into four phases. So initially, device initialization is a phase that is not a part of the protocol, but you need it in order to execute the protocol. So in a trusted environment, each of the devices is being provisioned with a device identity. And this identity can be, for example, a certificate, a pre-shared symmetric key, or a pre-shared public key. Think of this also in comparison to TLS as being one of the modes in which the protocol will be running. So each of the devices, depending on how they are initialized, also the way in which they authenticate one another or establish a session in the protocol is going to change. To actually bootstrap the protocol, the requester and the responder execute the VCA phase. And during this phase, they negotiate the protocol version, the capabilities inside of the protocol, and the algorithms that they are going to be using. So protocol version is the version of the protocol. Capabilities is, for example, can a responder encrypt the messages, or do they wish to mutually authenticate the requester? And finally, algorithms is, for example, the hash function that the parties agree to use throughout the protocol. Then, in the third phase, the requester gets to authenticate the responder and additionally to get some measurements of the firmware that they are running. And to do that, it can send multiple get certificates requests to get all certificates that the responder has been initialized with. Additionally, the requester can then challenge each one of those requests in order to prove the to authenticate the responder. And finally, then it can request for authenticated measurements and get them from the responder. And until this point in the protocol, all the messages here are sent in the clear, so there is no encryption happening. Which means that in the last phase of the protocol, the parties need first to execute a handshake or a key exchange between one another and then be able to continue sending messages within the secure session. Then, depending on the capabilities that they negotiated during VCA, they can also elevate the connection into a mutually authenticated one, can exchange application data that is confidential, and the integrity of the data is there during this application data phase. And if the session has been living for a long time, the requester can also ask for the keys to be updated. And once the parties wish to no longer continue the conversation in this session, the session can also end. And one thing to note here is that although we have represented the protocol here sequentially, in reality, the protocol is much more complex. So this means that while the requester and the responder are exchanging data in a session, at the same time, the responder can send another get certificate, receive a new certificate, and then start a parallel session with the responder. And while we were looking at the 200-page specification and this very complex protocol, and also looking at the major support that it has in the industry, we were a little bit surprised to see that it had received little to no formal verification. In fact, the only, let's say, formal analysis we could find at that point was a 3-page high-level stride analysis that gave mitigation suggestions such as use stronger hash function, use stronger message authentication codes, or digital signatures to authenticate one another. And to remedy that, then we decided to do a formal analysis of the protocol using the Tamar Improver. So the Tamar Improver is a formal verification tool that runs in the symbolic setting. And using this tool, then we were able to create 4 models for each of the SPDM modes, namely device attestation and each of the 3 key exchange modes. In device attestation, we included 3 phases, basically initialization, VCA, and the options, while for the key exchange modes, we included initialization, VCA, and each one of the potential ways in which the parties could run a session, meaning either with certificates, with the pre-shared symmetric key, or with the pre-shared public key. And all of these models then were evaluated against 3 attacker threat models. So first is the built-in attacker-controlled network, also called the Leviau network in the Tamarin tool. This means that the attacker can inject, drop, or modify any of the messages. Then additionally, we allow the attacker to also be able to register malicious certificates for any of the victims in the protocol. And finally, the attacker was also able to compromise the session key, and then we tried to see if we could still get some security guarantees on the protocol under such a strong threat model. So to give you an idea of the complexity of the protocol, these are some of the state machines that we were able to extract from reading the specification. They were not provided in the specification, but instead it took a long time to be able to, just from natural language, to get to these models. And here in the smaller box, we can see the requester and the responder to initialize their state, execute VCA, and then be able to spawn an unbounded number of parallel sessions. And in the bigger box is inside of each one of these sessions, the requester and the responder can then mutually authenticate one another, exchange an unbounded number of messages, update their keys, and then finally decide to end the session. In terms of an analysis effort, we roughly estimate the human effort to be 6 to 7 person-month of work. And there are also some statistics here. So our models range between 1,000 to 1,800 lines of code. We were able to prove 54 sanity traces for our models and also 6 helper lemmas. And in total, we could prove the 5 core security guarantees of the protocol. And these are our results. So for each of the models, we were able to prove some security guarantees. Namely, for device attestation, we proved unilateral authentication or responder authentication, and also the authentication of the measurements. And then for each of the key exchange modes, we could prove mutual authentication, the secrecy of the handshake key, and in addition, in a restricted model, we could also prove a version of forward secrecy inside of a session. In addition to our formal analysis, we were also able to identify several potential design pitfalls inside of the specification. So one of them is session ID size and optional responder nonce. So this means that there is a mode in the protocol where the parties might end up in a session that has the same, might end up in 2 sessions that have the same key. And this was due to the fact that the nonces inside of the protocol are actually optional, and the uniqueness of the key solidly depends on 2 bytes of session ID. Another design pitfall that we saw is that there are some requests and responses, vendor-defined request responses that are left completely unspecified, such that each one of the vendors can then decide if they have some special needs that they need their components to ask or to reply to. And as you can imagine, if the implementers might get this wrong, this also will then compromise the security of the entire protocol. Another example that we put here is also that there is no policy for remotely setting certificates. So at this point, if you authenticate with a component, then you're also able to set up a new identity for them. So to provide them with a new certificate, which is quite a strong ability to have, because otherwise the certificate would only be able to be provided inside of a manufacturing process. And in fact, we were able to identify several of such design pitfalls, but in the interest of time, I will spare you the details and instead refer you to our paper. So to conclude, we were the first to conduct a formal analysis of the security protocol and data model, version 1.2. We were able to prove some of the main security properties for each of the individual modes of the protocol, and also we were able to identify several of potential design pitfalls in the protocol. As our future work, we also press the need to have an analysis of the full composition. Due to SPDM being such a complex protocol and having all these sub-protocols, then there is a need to see that there is no interleaving between them that might lead to some problems. Additionally, we also did not include the underspecified functionalities or the functionalities that were left non-specified on purpose. All our works, so proofs and models, are made available, so feel free to check them out, and I'm more than happy to take your questions.